So hi everyone, today we're going to look at the second part of a harmonically excited vibration. So after completing this topic, we will be able to do the following. Find the response of an undamped and a viscously damped single degree freedom system subject to different type of harmonic forces. And we already done the response for undamped system. And today we're going to look at a viscously damped single degree freedom systems. And we'll be able to distinguish between transient steady state and the total solutions, understand the variations of a magnification factor and phase angles with the frequency of excitation and the phenomena of resonance and beats. Derive transfer functions of a system governed by linear differential equations with constant coefficients. Solve harmonically excited single degree freedom vibration problems using Laplace transform, and solve harmonically excited vibration response using MATLAB. Response of a damped system under harmonic force. So here we have a mass spring damper system. So this is also the system that we have used a lot in this class. And this system is subject to a force Ft that is equal to F0 times cosine omega t, which is a harmonic excitation. The first step, we're gonna find out the equation of motion. We can derive the equation of motion by using Newton's second law. So we will do the force analysis, take the block over here, and assume that it has a small displacement of x, and the force from the spring will be going up, the value that is k times x, and the damper will also have the force going up, which is c times x dot. At the same time, the object is subject to a force, external force Ft. Then we can write the equation of motion, which will be mx double dot, that is equal to the summation of all the external forces. Then we move the negative kx and negative cx dot to the left-hand side, will give us the equation of motion, mx double dot plus cx dot plus kx, that is equal to Ft. And since this equation is non-homogeneous, we know that the solution will be the summation of two parts, xht, which will represent the homogeneous solution, and xpt, that will represent a particular solution. The particular solution is also expected to be harmonic because the excitation Ft, that is a harmonic force. So we'll assume that it has a form of a xpt that is equal to capital X times cosine omega t minus phi. And since this is a damped system, we know that the response corresponds to the homogeneous solution that will die out eventually. So this will, xh is related to the part of mx double dot plus cx dot plus kx, that is equal to 0. So any initial condition excited vibration, it will die out eventually. So this is why xp, the particular solution, is also corresponding to the steady state solution. This is our equation of motion. And we also know that the particular solution xp have this form, and we are interested in the magnitude x and also the phase angle. If we know the magnitude and the phase angle, that will define the solution. So how do we get that? We're going to submit this particular solution to the equation of motion, which will give us this. Replace all the x in this formula by xp. So that will give us this equation. Expand cosine omega t minus phi, and we have sine omega t minus phi by using the two sine cosine formulas. The cosine omega t minus phi, which is equal to cosine omega t cosine phi plus sine omega t times sine phi, right? And the sine function of the summation of two angles is this. Sine omega t minus phi is equal to sine cosine minus cosine sine. Plug this result back into the above equation, that will give us two equations. How do we get the two equations? Because on the right hand side we have some magnitude f0 and some cosine function. For the left hand side to be equal to the right hand side, it requires the coefficient for this cosine function to be equal to f0 and the phase angle to be 0, right? So because for the right hand side, the cosine omega t, it doesn't have any phase shift, doesn't have like phi, right? So this is how we get this conclusion. Then from over here, we can further solve for capital X and also phase angle. So let's look at the equations. The first equation, that is x times some coefficient cosine phi plus something times sine phi. And the second equation, that is x times sine phi minus c omega times cosine phi. And if we use the square root of the first equation plus the square root of the second equation, so this is our first equation, this will be our second equation. The equation 1 square plus the second equation square, it will give us the formula of x. From the second equation alone, x times something that is equal to 0, and x we know that is not equal to 0, so that will give us the equation k minus m omega square times sine phi minus c times omega cosine phi that is equal to 0. So this will tell us that the tangent phi is equal to that, is equal to c omega over k minus m omega square. So now from the equation of motion, we already get this conclusion, right? So the next we are going to look at the magnitude and the phase angle individually. We copied the magnitude over x, that will be equal to force divided by square root of k minus m omega squared plus c omega squared. So we divided k on both the numerator and the denominator. So the numerator becomes f0 over k, and the denominator becomes, we'll have 1 minus m over k omega squared plus c over k omega squared. And further, we're going to use the previous conclusion that we have about the natural frequency. We know that natural frequency, that is a square root of k over m. And from that, we can find m over k. So m over k becomes 1 over omega squared. And similarly, we can find a c over k by looking at the definition of a damping ratio. The damping ratio is defined as the damping constant over the critical damping constant. The critical damping constant is represented by c sub c. And c sub c is equal to 2 times square root of mk. From that, we can find a c over k. So c over k will be equal to 2 times zeta times square root of m over k, and which is equal to 2 zeta times omega n. So we're going to replace these two terms by something that we found just now. So it will give us omega over omega n squared over here, and this term will also have omega over omega n. So now x becomes f0 over k divided by square root of 1 minus omega over omega n squared plus 2 zeta omega over omega n squared. And we know that both of the two terms have omega over omega n. We're going to further define the frequency ratio. The frequency ratio R is equal to the ratio of the frequency omega over omega n. And we know that a frequency omega, that is the frequency of an external force, and omega n, which is a natural frequency of the system. And we can further simplify it. X, that becomes f0 over k over square root of 1 minus r squared plus 2 zeta r squared. And further, we can use the definition that we had for static deflection. We know that f0 over k, that is defined as a static deflection. Delta, that is equal to f0 over k. Move delta st to the left hand side, it becomes x over delta st is equal to 1 over square root of 1 minus r squared plus 2 zeta r squared. All right, let's look at the phase angle. So from the previous discussion, we know that tangent phi is equal to c omega over k minus m omega square. And similar to what we did for the amplitude x, over here we want to write this in the form of the damping ratio r, not a damping ratio. We are going to write it in the frequency ratio r, in terms of the frequency ratio r, and see what we can do, about it. So the first step, we're going to divide it by k on both sides, on both the numerator and the denominator. So the numerator becomes c over k times omega. The denominator becomes 1 minus m over k times omega squared. Then we're going to use the conclusion that we got before about the natural frequency. So the natural frequency that is equal to square root of k over m. So we take a squared on both sides and flip them, so it will give us m over k that is equal to 1 over omega n squared. Further, we can find a c over k, because c over k showed up in the numerator over here, right? We're going to find that from the definition of damping ratio. So the damping ratio is defined as c over the critical damping constant c sub c, and c sub c that is equal to 2 times square root of mk, which will give us c over k, which is equal to 2 zeta times square root of m over k, and further become 2 zeta divided by omega n. So we plug this value in and further replace the ratio omega over omega n by r, so will give us the conclusion. Tangent phi becomes 2 zeta r over 1 minus r squared. So given this mass spring damping system, the particular solution have a form which is harmonic. The frequency depends on the frequency for the external force, and the magnitude x over the static deflection delta st, that is equal to this, and the tangent phi is equal to 2 zeta r over 1 minus r squared. And over here, x over delta st, this is the definition of a magnification factor, or we can also call it an amplitude ratio. So then we want to see like what happens by plotting them out. So we're going to plot the relationship between the frequency ratio r and the amplitude ratio. So the x-axis is the frequency ratio. So the result will be get from the first equation over here. So let's look at an extreme case. When the frequency of the force is very small, so it means r that is a very small number. Let's see what happens. If r is very small, by looking at this equation over here, r is very small, this r squared becomes very small. Something 1 minus a very tiny number become 1, right? Here 2 times the r, that is also negligible. The amplitude ratio in that case become 1. So this is why at the beginning, when the frequency of the force is very small, the amplitude ratio is almost 1. So this is why we started from the 1. And as we move on, if the frequency ratio is very large, say r is a very large number, the first term on the denominator, that 1 minus a very large number squared plus 2 zeta times r squared. Denominator become very large number. So this is why the amplitude ratio become 0, right? So this is what we see from the plot. You start from 1 and eventually the amplitude ratio become almost 0, right? When the frequency ratio is equal to 1. So by looking at it from here, the frequency ratio is equal to 1. 1 minus 1, that is equal to 0, right? And over here, it becomes 2 zeta times almost equal to 1. So that becomes 2 zeta squared. So that becomes 1 over 2 zeta. If r is equal to 1, the amplitude ratio becomes 1 over 2 zeta. And if zeta is a very small number, which is indicated by this curve, when zeta is equal to number, very small number, we know that the amplitude ratio becomes very large. So this is why we see a huge peak over there. And as zeta increase, the peak will decrease. We see peak decreases if z is equal to 0.3, and if z is equal to 0.4, the peak becomes smaller, and z is equal to 0.5, it becomes even smaller. So this is what we can see from the frequency ratio versus amplitude ratio plot. The next, we want to see what happens to the phase. So again, in the second phase plot, the x-axis is the frequency ratio, and the y-axis is the phase angle. Let's look at the first extreme case when the ratio is very small. And when r is a very small number, 1 minus r squared, that become 1, right? It becomes 2 zeta r. So it's very small. So if r is very small, it starts from a very, very small number. So this is why we see the phase angle always start from almost 0. And let's see another extreme case when r is very large. When r is very large, this bottom becomes very large number. It's a negative. It becomes 2 zeta times r divided by minus r squared. So it becomes minus 2 zeta divided by r, which is almost 0, but it's a negative number. The inverse tangent of a negative number, but it's almost 0. So we see that is close to 180 degrees. So this is what we see from this region. When r is very large, and the phase angle become almost 180 degrees. And let's see another case when the frequency ratio is equal to 1. What happens? So when that is equal to 1, the denominator here is 1 minus 1. That is very close to 0, right? 1 minus 1 is equal to 0. And 2 zeta r divided by something that is very close to 0, we know tangent phi is equal to infinity. Tangent phi is equal to infinity. It implies the phase angle phi is close to 90 degrees. This is what we see from this dot. Connect the rest together, it will give us this type of plot. So the phase angle will change from 0 to 180 degrees, and depends on the damping ratio, the rate of change will be different in the region close to frequency ratio is equal to 1. So when the damping ratio that is a very small number, we see the phase angle changes very quickly near the frequency ratio is equal to 1. And as we increase zeta, we'll see that it increases at a slower rate. And we further increase that, you will see it become flatter and flatter and even more. So next, quality factor and bandwidth. So for small values of a damping ratio, zeta that is, let's say, less than 0.05, then we can find the magnitude, which is something we did, right? The amplitude ratio becomes 1 over 2 zeta. And 1 over 2 zeta over here, we define it as a Q factor or quality factor. In analogy with some electrical engineering applications, such as the tuning circuit of a radio, when the interest lies in an amplitude at a resonance that is as large as possible. This Q factor defines basically how much the system will amplify the vibration. And by giving the Q factor, we can further define the points where the amplification factor falls to Q over square root of 2. And these are called half power points. We already know that at a Q factor, it represents a frequency where the frequency ratio is equal to 1. And beyond that, we find 2 places where the magnitude is not as large. The magnitude is equal to Q over square root of 2 of the magnitude from Q factor. And these are called half power points. And why these are called power points? Because of the definition of the power absorbed by a damper, which can be calculated using by pi times c times omega times x squared. So when x becomes square root of 2 times x max, we know that take a square term of that give you half a power point. So this is why it's called half a power points. Let's find these half a power points. So to find the half a power points, we just need to let the amplitude ratio x over delta st to be equal to 1 over square root of 1 minus r squared plus 2 zeta r squared, that is equal to half of power points, which has a magnitude amplitude ratio of q over square root of 2. And we also know q, that is equal to 1 over 2 zeta. So which will give us 2 over square root of 2 times square root of 2 times zeta. So we solve this equation, which will give us the two solutions. One solution is r1 squared, that is equal to 1 minus 2 zeta. And the second one is r2 squared, that is equal to 1 plus 2 zeta. So if we have r1 and r2 like that, then we can further replace r1 by omega 1 over omega n, r2 that is equal to omega 2 over omega n, right? We replace that. We use this first equation minus the second equation will give us omega 2 squared minus omega 1 squared. That will be omega 2 over omega n squared minus omega 1 over omega n squared. So that will be equal to 1 plus 2 zeta minus 1 minus 2 zeta. That will give us 4 zeta. And multiply omega n squared on both sides will give us omega 2 squared minus omega 1 squared, that is equal to 4 zeta times omega n squared, right? So this is how we get the first equation. And this can further, omega 2 squared minus omega 1 squared can be further broken down into omega 2 minus omega 1 times omega 2 plus omega 1. We also know that omega 2 plus omega 1, which is the 2 points on the two sides, and if we add them together, it'll become 2 times omega n. So in that case, we can find omega 2 minus omega 1. So omega 2 minus omega 1, that'll become 4 zeta times omega n squared divided by 2 omega n. That will give us 2 zeta times omega n. So the difference between the two frequencies, which is also called a bandwidth. So over here, this is called a bandwidth. So the Q factor, or the quality factor, is the peak. If we look at the amplitude ratio, that is a peak. Half power points have a magnitude that is equal to Q divided by square root 2, which will give us 2 points. And 1 point represent omega 1, and the other points represent omega 2. So the difference between the frequency, that is equal to 2 zeta times omega n. So 2 zeta times omega n is bandwidth. So basically it tells us that what will be the frequency will be allowed for the system to pass.